Some recent brain studies raise questions about how cleanly we can draw the line at death, almost as if the signal keeps pulsing after we think it's gone, like a Wi-Fi network you didn't realize was still connected. This isn't coming from mystical language, but from 2025 neuroscience research, including a documented case in Frontiers in Aging Neuroscience, where continuous EEG recorded structured brain activity moments after clinical death. Those results pushed me to look at the rest of the data: patterns in perception, changes during grief, and quantum correlations in human consciousness labs, until one moment forced me to stop and question everything I thought I knew. The moment science got uncomfortable. For Dr. Tara Swart, the turning point didn't arrive in some dim, high-security lab, but in the plain light of an ordinary morning. Coffee cooling next to her, she opened a fresh dataset from a brainwave monitoring system. The patient's chart showed every medical sign of death: no heartbeat, no breathing, no brainstem reflexes. By every conventional teaching in neuroscience, brain activity should have been absent. Yet there, in the compressed readout, appeared slow, deliberate pulses. Not random electrical noise, but structured patterns appearing where nothing should be. They didn't resemble the chaotic bursts seen in seizures or the decay of neural tissue. In documented cases like these, the patterns fell outside anything she had been trained to expect. And they raised a bigger question: what exactly unfolds in the brain at the threshold of death? Initial suspicion fell on the equipment. Electrodes pick up interference, software misreads data, recordings can be contaminated by mechanical artifacts. But the consistency, even across separate occasions, made purely technical error harder to defend. In one instance, she heard a senior colleague quietly suggest setting it aside as post-mortem noise. It was a polite term that dismissed without explaining, illustrating what she already knew from her own field. Some subjects carry an invisible, do not touch warning because of the professional risk they bring. By early 2025, hints that her observations might be part of a wider pattern cropped up in the literature. The most prominent came in a controlled case study published in Frontiers in Aging Neuroscience, led by Dr. Ijmal Zemma, with collaborators from the University of Louisville and the University of Tartu. In it, continuous EEG recorded coordinated changes in brain oscillations during the 30 seconds before and after cardiac arrest. Across gamma, delta, theta, alpha, and beta bands, the shifts were organized, not chaotic. Zemma speculated that in the living, gamma waves often relate to processes such as dreaming, memory recall, and sensory integration, raising the startling possibility that, in those final instants, the brain might be re-engaging similar networks. It was just one patient, under very specific monitoring circumstances, but paired with later reports in 2024 to 25, including results published in the Journal of the American Medical Association, noting functional connections between early visual areas and frontal regions moments after death. The single case was enough to destabilize the textbook binary between alive and gone. These later accounts remained provisional, requiring replication. Their authors avoided any claim about consciousness persisting. At most, they showed the brain doing something more complex at life's endpoint than an immediate shutdown. For Swart, this positioned her work uncomfortably close to the cultural taboo she had long been aware of. She often repeated that in scientific circles, anything that brushes against life after death is treated with suspicion, and talking about it creates reputational danger. She had even been part of psychiatric teams earlier in her career that treated reports of after-death contact strictly as symptoms to be managed, not as data to be explored. Now, faced with her own findings, she knew that ignoring them for safety's sake would also be unscientific. The context mattered. These organized oscillations challenge the simple on-off model of the dying brain, but they do not by themselves prove any ongoing subjective awareness. Elevated gamma activity could mean many things, among them the possibility, as Zemma suggested, of a last replay of life events. It could equally reflect non-conscious processing as chemical gradients and network dynamics collapse. The key was not in declaring what it must mean, but in tightening the methodology enough to find out. In the early 2020s, advances in imaging down to the scale of single neuron clusters and more precise cross-validation protocols had raised the bar on what counted as solid evidence in neuroscience. In the 2025 Frontiers case, signals were measured not just for presence, but for coherence, the degree to which distant brain regions stayed in sync. This coherence, however fleeting, stood out because it directly conflicted with the assumption that, once circulation stops, neurons very quickly lapse into disorder. The JAMA findings added to the nuance by showing how sensory and associative areas might stay functionally linked briefly after death, hinting at a possible shift in how researchers understand consciousness, decoupling it, in part, from strictly frontal lobe processes. Still, many in the field interpreted the activity as residual reverberation, the last coordinated echo of a network losing equilibrium. Others posited that certain microenvironments, such as regions with higher tolerance for low oxygen, might allow activity to persist longer in some individuals than others. But none of these interpretations closed the discussion. In candid, off-record conference exchanges, experienced researchers admitted that these readings didn't slot neatly into existing models. Swart approached those conversations cautiously. She avoided phrases that could be seized on as sensational, anchoring every public statement to measurable results. Her goal wasn't to persuade her peers that the mind continues after death, but to carve out space where recording and publishing anomalous post-death data wasn't immediately career-ending. If history had taught neuroscience anything, it was that uncomfortable data often precedes shifts in understanding. Neuroplasticity, gut-brain independence, and mirror neurons had all once sat at the fringes before becoming accepted. What separated these recent findings from earlier, less rigorous accounts of strange brain activity after death was the context in which they were made. Continuous, high-fidelity recordings, independent verification, and careful peer review. Yet even with that foundation, the evidence remained at the level of intriguing fragments, not established law. That's why Swart insisted that the takeaway, for now, was about complexity, not certainty. The brain's final moments aren't a hard stop. They may involve ordered processes we've barely begun to map. But whether any of that order contains experience is still unknown. Framing it that way mattered, not just to keep the science intact, but because the implications touched human concerns well beyond the lab bench. If death isn't the hard line we thought it was at the neural level, then our understanding of end-of-life care, grief, and even the ethics of organ donation could shift. Swart believed that letting in a broader conversation about what these signals might, and might not, mean was the first step. And it was a step she was willing to take despite knowing how quickly colleagues might retreat from proximity to such work. The real payoff, she often noted, wouldn't come in the form of a single, definitive answer. It would come in building a clearer, more balanced view of what the science actually says so far, and in offering people ways to integrate that understanding into both their professional practice and personal lives. For viewers following along here, the next part of our story will open up a different question. If our sensory world is larger than we were taught, then the boundary between the known and the unknown, in life and perhaps in death, may be far more porous than most of us have ever considered. From 5 senses to 34, and now 37. Most of us were taught a tidy chart in school. Sight, hearing, touch, taste, and smell. Maybe, if the teacher wanted to be intriguing, there'd be a passing nod to a so-called 6th sense. The way it's presented makes it sound final, as if those 5 cover every possible route by which the brain gathers information about the world. But that picture is far from complete. Researchers have been expanding the sensory map for decades, and by 2025, voices like neuroscientist Dr. Tara Swart had brought widespread attention to a much broader count, a framework listing 34 distinct human senses. It's not mystical in origin, but built on measurable, physiological systems, including many that operate without us being consciously aware of them. Scientists increasingly agree that the 5-sense chart is a simplification. If you count each internal physiological sensing stream as a perceptual system in its own right, the list grows quickly. Proprioception, for example, gives us a constant map of where our limbs are in space without needing to look. Interoception monitors everything from gut contractions to heart rhythms, feeding the brain status updates that can influence mood, decision-making, and even intuition. Chronoception provides our internal sense of the passage of time, shaping how we anticipate events and coordinate movement. Other well-established sensory modalities include nociception, pain, thermoception, temperature, equilibrioception, balance, and chemoreception, detecting chemical composition in the blood, such as pH shifts or oxygen levels. These are not exotic or fringe ideas. They are rooted in mainstream neuroscience. How you arrive at a number like 34 depends partly on taxonomy. Some researchers group related processes together, others split them into finer submodalities. Interoception alone can encompass multiple signal types. Stretch receptors in the stomach, baroreceptors tracking blood pressure, osmoreceptors monitoring fluid balance. If each is counted separately, the total grows. Swartz framing is essentially an expansionist proposal, a way of reminding people that what we call perception is not limited to what we can deliberately notice. It's an attempt to catalogue the genuine diversity of the information streams feeding the brain at any given moment. Crucially, many of these senses function in the background. Proprioception runs without interruption, allowing actions like walking or typing without conscious calculation. Thermoception quietly drives behavioral choices, stepping into shade or reaching for a jumper, often before we think about it. Even changes in blood CO2 levels can prompt adjustments in breathing rhythm well before the feeling of breathlessness hits consciousness. These are continuous inputs, functioning as part of what shapes our lived reality, without showing up as a distinct feeling we can name on demand. Placing these alongside the 5 traditionally taught senses reframes how we think about perception. The brain is not a passive receiver of 5 fixed channels. It's an integration hub for dozens of sources, both internal and external, many of them silent to conscious awareness. If emotional or environmental conditions change the weighting or reach of these channels, the patterns of perception that result may feel unfamiliar or heightened. That opens the door, cautiously, to hypotheses about unusual experiences, without stepping outside the boundaries of established sensory physiology. This is where speculation, clearly marked as such, comes in. If certain states, intense focus, meditative absorption, or powerful emotions, alter how the brain samples and integrates these multiple sensory streams, then it's reasonable to ask whether inputs usually below awareness might briefly surface. Such moments could create the impression of picking up on information that seems to arrive out of nowhere. Documented research already shows that emotional state can influence bodily signal processing. For example, heightened interoceptive accuracy under stress, or altered time perception in moments of fear. Extending that logic to more subtle forms of perception is intriguing, though any link to experiences outside ordinary life needs replication and rigorous control. What's important is separating the physiology from the interpretation. The existence of 30-plus senses, as physiological systems delivering information to the brain, is well supported. The idea that those senses could, under the right conditions, contribute to impressions some interpret as extraordinary is still a hypothesis. But the sensory expansion work forces a rethink of our assumptions. Much of what guides behavior and shapes experience is happening outside the conscious, 5-sense model. If you visualize this broader sensory map, it's not a simple list, but an overlapping structure. External senses like vision and hearing feed into multimodal hubs in the brainstem and cortex. Internal senses like interoception and proprioception constantly update those hubs with the body's status. Chemical sensing, thermal gradients, balance. All these contribute to a moment-by-moment state estimate that lets the brain predict and react. In this model, perception is less about passively recording what's out there and more about actively constructing a working model of reality from dozens of inputs. This structural view matters for any discussion about altered perceptual states. If the brain's construction process can adapt, skew, or open under certain mental or emotional conditions, then what we experience as more vivid, strange, or unexpectedly clear perception might be rooted in measurable shifts to that integration process. Physiological senses that are usually quiet could, briefly, become more prominent in the overall picture the brain presents to itself as reality. Swart and others see the 34-sense framework as more than an academic curiosity. It's a reminder that human perception is an intricate, distributed system, one in which awareness is only the visible tip. The idea encourages a more generous view of what the brain might be doing in moments that feel out of the ordinary. And it's here that the conversation often moves toward the role of personal experience. When and how changes in this sensory integration map might intersect with life events powerful enough to reconfigure it. Because there are certain situations where something does appear to shift, not over decades of evolution, but in the space of weeks or months. It's not a laboratory-induced state or a biohacker's project. It's something people encounter in the course of ordinary life, often without warning, and it can leave them sensing the world in ways they hadn't before. How grief rewires the perceptual brain. When loss strikes, the emotional weight is obvious. But neurologically, grief functions as a reconfiguration. a process that reshapes how the brain processes and prioritizes information. Imaging studies over the past 2 decades, from early work by Gundel and colleagues to Mary Frances O'Connor's 2012 research, show that grief is not confined to emotion processing regions alone. It engages a wider network: emotional memory hubs such as the posterior cingulate cortex, the insula's interoceptive and emotional awareness circuits, and reward-related areas like the nucleus accumbens. During grief-related stimuli, these regions show heightened activation and altered connectivity, suggesting that perception itself, the sorting of what is signal and what is noise, is being recalibrated. In some individuals, this recalibration appears as a lowering of sensory thresholds. Experimental designs using faint auditory or visual patterns have found that recently bereaved participants can detect subtle cues more often than non-bereaved controls. Instead of discarding low-level sensory data, the brain seems more inclined to retain and route it into conscious awareness. Researchers describe it as a shift in gain control, with the system amplifying inputs that might normally be ignored. The result isn't supernatural. It's measurable changes in how sensory integration hubs operate under stress and attachment-related disruption. The insula's increased connectivity with sensory cortices is one example. This hub ordinarily filters and integrates internal bodily signals, heartbeat, breath, visceral states, with external cues. Under grief, that filter appears more permissive. The posterior cingulate, central to autobiographical memory, also shows stronger links to emotional and perceptual networks, perhaps explaining why reminders of the deceased, even fleeting, indirect ones, can feel immediate and vivid. Laboratory findings echo personal accounts. Some bereaved individuals report being attuned to tiny environmental shifts. A change in airflow in another room, a distant rhythmic sound masked for others by background noise, a flicker in peripheral vision. These perceptions align with known changes in the balance between emotion-driven networks and top-down regulatory regions, like the prefrontal cortex. O'Connor's work suggests that this altered state may be an adaptive mechanism. In disrupted environments, heightened sensitivity could aid survival by capturing more potentially relevant information. The depth of the relationship matters. Imaging analyses indicate that people with stronger emotional bonds to the deceased often show more pronounced neurofunctional changes. Enhanced crosstalk is observed between limbic regions, where emotional salience is processed, and prefrontal areas that direct attention and decision-making. This may underpin why certain cues, whether linked directly to the person or symbolically associated, capture attention so readily during early bereavement. Grief also triggers systemic physiological changes that may feed back into perception. Research points to fluctuations in neurotransmitter systems, dopamine, serotonin, norepinephrine, associated with motivation, emotional tone, and alertness. While exact neurochemical cascades remain under study, O'Connor and others note that inflammation and immune responses are consistently implicated in grief physiology. Stress-induced inflammatory processes can influence brain function, possibly altering connectivity and the efficiency of neural signaling. The specifics of how these peripheral changes shape sensory integration are still being explored, but the link between acute stress, systemic responses, and altered perception is grounded in established biology. An unexpected parallel has emerged between certain grief-related brain states and those seen in altered consciousness practices. EEG and fMRI studies show that some grieving individuals exhibit patterns reminiscent of experienced meditators or trance practitioners. Elevated gamma synchrony across distant cortical areas, stronger alpha, theta coupling, and distinctive thalamocortical resonance. These patterns correlate with inward focus, modified time perception, and richer cross-modal integration. Models like Nelson's Neptune framework make the case that REM-like intrusion into waking states may help explain both some near-death experiences and pockets of unusual perception during profound emotional disruption. The resemblance doesn't confirm any non-local awareness, but it does outline plausible neural conditions for atypical experiences. Established clinical phenomena also remind us of the brain's capacity for the unexpected near the edges of life. Michael Nam and Alexander Bathiany's documented cases of terminal lucidity, where severely impaired individuals briefly regain clarity shortly before death, show that the nervous system can shift into different operating modes even late in decline. While distinct from bereavement, these cases underline that sudden, striking changes in cognition or perception can arise from transient changes in brain network dynamics. What does this look like in day-to-day life after a loss? Attention patterns tilt toward relevance for anything tied to the deceased. Eyes may scan familiar handwriting faster than other scripts. A trace of a familiar scent can halt movement mid-step. Acoustic changes in a space where the person once moved might provoke orientation before conscious recognition happens. From a resource perspective, this mode is costly, metabolically, because heightened sensory gain demands energy, and emotionally, because every detection is freighted with significance. These changes are not permanent for most people. Longitudinal imaging shows a trend toward baseline activity within 6 to 12 months, although some retain subtler shifts in sensitivity for longer. A few, often those who engage in ongoing contemplative or body-focused practices, may stabilize elements of the heightened integration beyond the acute stage. For them, grief effectively opened a door to a perceptual mode they later maintained intentionally. The overlap between this bereavement-induced state and intentional altered states offers one possible reason why post-loss anomalies, sensations of presence, vivid dreams, perceptions difficult to explain, are disproportionately reported in the weeks and months after a death. The nervous system, during that time, is already configured for greater integration across sensory and emotional channels, with less aggressive filtering by executive control systems. Whether the content of those moments originates internally, as a synthesis of cues and memories, or from an external source remains a matter of perspective and investigation. What is less in doubt is that grief modifies the very architecture of perception. This reconfiguration is why, in certain contexts, the boundary between ordinary sensory detection and experiences interpreted as extraordinary can blur. It creates conditions where small anomalies stand out, and where meaning is more readily attached to fleeting inputs. And it's within this neurobiological landscape that some turn toward practices or people who claim to mediate between the living and the dead, bringing us to another area where measurable data and contested claims intersect. What the new data says about mediumship accuracy. For many people, the default image of mediumship comes from television or stage shows. Broad guesses dressed up as revelation, plenty of prompting for clues, and an audience primed to agree. That stereotype makes mediumship easy to dismiss as theater. But when you move away from performances and look instead at certified, experienced practitioners working under strict experimental conditions, the results become harder to account for by performance tricks alone. In the past several years, a number of research groups have applied protocols designed to strip out all the usual paths for information leakage. A recent meta-analysis covering studies from 2001 to 2019, and only including those with the tightest controls, found modest but statistically reliable effects. Mediums performed roughly 6 to 14% above chance in high-control experiments. Under certain triple-blind protocols, the effects in individual studies were larger. One replication published in Explore reported that sitters correctly chose their intended readings 65.8% of the time, compared with 50% expected by chance. Another analysis found that those intended readings contained about 29.5% more correct statements than matched control readings. These numbers are not a blanket claim for all mediumship, but examples where performance exceeded what random guessing could produce. The methodology behind these findings is important to understand. A triple-blind protocol means the medium does not know who the sitter is. The sitter does not know which of 2 or more transcripts was meant for them. And wherever possible, the experimenters who handle the scoring step are also unaware of the match. In some setups, the only information given to the medium is the gender of the deceased. The reading is conducted without any live cues, often over anonymized phone lines or recorded offline. The transcript is later scored by a pool of sitters, none of whom are told in advance which reading is theirs. This approach removes the possibility of tailoring statements to immediate feedback, and it limits the influence of subtle prompts a sitter might give without realizing it. At the Windbridge Research Center, this framework is pushed further through a 5-level blinding strategy. All contact between mediums and sitters is removed. Even brief audio interactions are anonymized, and recordings are transcribed before the sitters score them. The intention is to close every channel, verbal, visual, or behavioral, through which information could travel in ordinary ways. In a dataset of 58 readings from 20 certified research mediums, scored by 116 sitters, the results provided statistical evidence that accuracy exceeded conventional explanations. Certified mediums tended to score higher than non-certified ones, suggesting that training, skill, or specific aptitude influences results. When accurate information appears, it often falls into several categories. The first are identifiers, habits, physical traits, or characteristic phrases that fit one deceased individual clearly. The second are references to events in the sitter's life that took place after the person's death, which are difficult to attribute to cold reading because they require no immediate feedback. The third are message-like statements, personalized sentiments or acknowledgements tied to shared experiences. While mainstream interpretation allows for coincidence and inference to account for some successes, the repetition of certain patterns, especially post-death event mentions, remains a challenging feature to reconcile with the conditions. Even so, most scientists in this area are careful with their conclusions. Above-chance results on their own do not prove that mediums are in contact with the consciousness of the dead. Competing hypotheses include information access through some kind of psi process that does not involve the deceased, or other, less explored cognitive mechanisms. Critics point out that small samples and the challenges of replication mean larger, pre-registered studies are still needed. The data so far establish that something is happening beyond random guessing under conditions designed to remove normal sensory routes, but they leave open the question of how. Context may also play a role. Some researchers have noted variations in medium performance linked to factors such as physical setting, mental preparation, or emotional state. These observations have prompted exploratory studies to test whether certain environments or pre-session activities influence outcomes.